Okay, so just, I don't want to take a lot of time talking. Everything in this problem is explained, I hope, very clearly within the notebook. I will just say two things really quickly. So we're going to build a Metropolis Hastings sampler. This is a form of an MC-MC algorithm. I know that these terms have not been perfectly defined for you yet. The brief idea, though, is that you're just going to generate a lot of different points within the posterior as an estimate for the total posterior. Okay? The way that you go about generating those estimates is described fully within the notebook. I'll be walking around. I know that things are a little bit tight in the center section now, so because we are working, feel free to spread out within this room. However, I will be just flashing up solutions as we go so that hopefully no one gets stuck. And if you do decide to move from the center section to a side section, make sure that you go with a partner, okay? Because everything we're doing within the DSFP is with a partner. All right, thank you. Okay, we are a few minutes before the break, so I just want to go over everything really quickly. A lot of times I just kind of click through everything, and I think I end up going way too fast, and no one really understands what's happening. So I'm going to do a short interpretive dance to try to explain to you how the Metropolis Hastings algorithm works. Okay, so the idea is as follows. If you have some large multidimensional space that you're trying to integrate, as we are when we're using techniques like MC-MC, you start at some point, right? So I'm going to measure points with my fist. So you start at some point, theta naught, and you estimate the posterior at this point. Okay? So now from here, you need to step somewhere else within your parameter space and figure out if your new position is more likely or less likely than where you started. Okay? So we're going to propose, and now is when I need 3 hands. We're going to propose moving over here. All right. Now, in looking at that proposal, if the new step is more likely, meaning the posterior value is larger than the previous posterior value, then you take that step every single time. And this is a good idea because you want to find the maximum of your probability distribution. So anytime you can increase the probability, you want to do that. So every single time the probability increases, you take that step. Now, suppose I'm here and I want to take a step over here. Okay. That step will actually lower the probability. Okay. That is not necessarily a bad thing. Right? So imagine for a moment that you have some multimodal distribution and you're sampling near a local maximum, but not the global maximum. Okay. So in Metropolis Hastings, to understand whether or not you take this lower probability observation, you draw a random number between 0 and 1, right? And you compare the ratio of the posterior values to your random number between 0 and 1. And if that ratio is higher than your random number, then you take this step in the direction of lower probability. Okay? So on average, you will only move in the direction of higher probability, but it is possible to move in the direction of lower probability. And we'll talk more about the mathematics of MC-MC tomorrow, okay? But what this means is that if you take many steps, okay, you can actually go from any point to any other point. Now, this might require some luck in the sense that your random number generator is going to have to spit out a bunch of very low numbers consecutively, but that can happen. Right? And so this is a critical difference between something like MC-MC and something like SciPy optimize, which is just going to say, move me in the direction of higher likelihood, right? Maximum likelihood at every step. Just move to whatever's the highest. And then once you get to essentially a local maximum, you stop. Right? That is a difference between MC-MC and that approach. Okay, so I think we all got through the calculations in problem 2. I'm going to within, yes? Okay, so within problem 2, we did things like compare what the values of the likelihood, the prior, and the posterior are if you are at the exact correct answer, which we know because we have simulated this data, or if you, as you move away from that, what do you get, right? And so here's just an example. As you move to the exact correct answer, you get a larger number, meaning more probable, meaning good, all right? And if you're outside the bounds of your prior, then you get negative infinity because the probability is 0. Okay, all right. So going quickly so we can get to the break. So I just described what Metropolis Hastings is, and you can read a sort of more concrete definition in the problem. So one of the things you have to test, as I said, is what is the ratio of the likelihoods at your 2 different steps. So this is what we did with the Hastings ratio function. Okay, and then we did some examples of how the Hastings ratio compares at a few different positions. I'm just going to skip over that for now. Okay. All right, so then the next problem was to actually write out the function that does the Metropolis Hastings MCMC. So sorry, if you haven't seen the sort of text that's in red before, so cohort 4 or auditing students, this is something that's called Docstrings. Any of the sort of main Python packages that you use have this. It's a very useful way of briefly documenting what it is that your code does, right? So we have definitions of all of the variables that go into the code. We also have definitions of what is returned from the code, right? And this is a very, very useful, relatively low overhead way to keep track of what is happening in any function or class that you build within Python. Okay, so this is the most complex piece of code in the notebook, but we're going to create an array, positions, which is going to keep track of everywhere that we're stepping through our space. And then we're going to have another array, which is the log of the posterior at every position, okay? And then we also want to keep track of, and this will come into, we'll really understand why this is important tomorrow, but we want to keep track of the acceptance ratio, which is just how often are my proposed steps being accepted, okay? And algorithmically, as you might imagine, you want an acceptance ratio that isn't very, very low, because if it's very, very low, what's going to happen is you're going to have to wait a long, long, long time to actually move around the space and get some estimate of what the probability is. Okay? And we'll talk about what low and high is for the acceptance ratio tomorrow. Okay? So we're going to start at theta 0, so just some guess. We just pick any point within the space. That's where we're going to start. All right, we calculate the posterior at that point. We then propose a jump to some new point based on some Gaussian distribution that we have provided. We calculate the Hastings ratio. We calculate R, the random number. If the Hastings ratio is greater than R, we have accepted this. We add the new position to the chain. We add the posterior to the posterior array, and we update the acceptance ratio as being higher than it was before. Okay? If instead, I cannot scroll, sorry if you can't see the bottom. If instead H is less than R, we still add to the chain, but what we're adding to the chain is the current point. All right? With the same posterior we had previously, and then the acceptance ratio drops down slightly. Okay. All right. So now the next thing was to run this, which doesn't show anything, but you get results now. Okay. So what does the chain actually look like? What is happening? So here is M versus B. We started way down here at a slope of 2.7 and an intercept of minus 60. Okay. And each of these points is slightly transparent. So if you see a dark point, such as the very first point here, okay, what that means is that there's actually multiple steps at that position. So the first proposal from this point was actually rejected from the starting point here. The second one was accepted. We moved here. Accepted, moved, one rejected, okay? And we just trace all around until eventually we get close to the maximum of the posterior. And then we're sort of bouncing around the probability distribution here, right? So the red star is the answer in this case. And the lines are showing us how this thing has moved through this space. Okay. Another way to visualize this is to actually color each of the individual observations by the value of the posterior at that observation, right? So you can see where we started, dark purple. This is actually very unlikely. And then as the chain is moving, we're getting more and more likely. until eventually we're sort of sampling around the maximum, which is the bright yellow values here, close to the true answer itself. Okay. All right. So that's it. All right. I know that not everyone got quite this far, but just a little bit more work. And that function that I showed you, right, this algorithm, does the Bayesian integration that David was talking about earlier today. Okay. All right, there's a few other things I just want to show you. Okay, so there's some stuff that is hard to know, and we're going to talk about this in more detail tomorrow, right? But why did I say do 500 steps? I don't have a particularly good answer for you, right? But you should be thinking, how many steps do I need to do? 10 is way too few, as you'll see here in a second. Oh, sorry, okay. 3 choices that were made. So why 500 steps? Can you do fewer, or do you need to do many, many more? All right, we'll answer that tomorrow. Okay. What about the widths of the Gaussian distributions that are used to decide how far away you're going to move from here as you are proposing different points that you might move to? Right? Why did we choose that? Again, we'll talk more about how to optimize that tomorrow. And then finally, why did we actually start at 2.7 and negative 70? Right? These are all just weird choices that we happen to do. So what happens if we make some different choices? So this is a function that puts together the 2 plots that I showed you a moment ago. So let's instead run the chain for 50 steps instead of 500. What does that look like? Okay. So with the short chain, we don't actually manage to explore the region of maximum probability. Okay. So short chains essentially are never a good idea. Okay. With an incredibly long chain, things maybe are starting to get a bit redundant, right? So this is 5,000 steps instead of 500, and we just have many, many, many points near the maximum. Okay. Now again, we may technically still need more than 5,000, but there is always a point when you're essentially at overkill. You do not need to keep going, all right? Okay. What about if we change where we start? What if we change our proposal distribution? So what if we use a very, very small Gaussian? Okay. So this means each of our proposed steps is very close to where we started, and you can see in 500 steps, right, the chain doesn't actually travel particularly far. What if we use a wide Gaussian? Okay. So what's happening in this case? The chain does, in this case, actually get close to the maximum probability, all right? But what you can see is that there's very, very few points. And that's because with this wide Gaussian, many of the proposals are very, very far away from the maximum probability, and so everything is being rejected. Okay. All right. And then finally, what about where you start? So what if we start really, really, really far away? So in this case, at a slope of 30, which is significantly higher than the true slope of the line, and you'll see there's no movement at all, because every proposed step in this case is rejected. Okay. So thinking about where to start does matter. Okay. What if we start at some very, very low slope? Okay. You will see that still eventually we can get over to the correct answer. Right? So all of these are things that you should take under consideration, and you should be thinking about them as we talk about MCMC tomorrow. All right. Okay, finally, I just want to show a helper function, which might be useful. So tomorrow, the problems that you will do will essentially be an implementation of the algorithm that we wrote today. And I created a quick sort of summary plot for a 2-parameter problem. So more work would have to be done if you have larger parameters than this. All right. So the summary plot shows the following. And this is one way that you can diagnose the quality of your MCMC. So here we have a hex bin or a 2D histogram of all the posterior samples. All right. Here we have different draws from the posterior, so the different models, how they actually compare to the data. And then over here is what's called the trace plot. We'll talk about all of this more tomorrow. Okay. So ideally, your trace plot will not have strong correlation in it. All right. We see there is strong correlations here. Your models will match the data pretty well. Okay, that's not so bad in this case. And then the sort of maximum of your posterior samples will be close to the correct answer in the case where you can simulate things and you have the correct answer. Okay. All right. So I messed around a little bit, tuning the parameters, in particular changing the Gaussian, and running 50,000 steps. So many, many more than what we had before. You get something that looks like this, and I contend this is really good. This is about as good as you will do. Okay? All right. Pause now and ask if there are any questions. Yes. Yes. So the solutions for both of the notebooks from today will be posted this evening. One thing I will note is that we do not assign homework in the DSFP. That being said, of everything that you have ever done in the DSFP, those of you in cohort 3, and for those of you that are new, looking at the solutions for this notebook before the rest of this week will make a huge difference if you did not get this far, okay, which I think is more or less everyone, will make a huge difference in how well you will understand what's happening in the notebooks tomorrow and the days after. Okay? So this is the one time when it really, really, really matters that maybe if you can, you spend a little bit of time this evening looking at the solutions, right? Or this morning, okay? We're gonna give you the function, so you're not gonna have to rewrite the function tomorrow, but you'll be applying it to more interesting problems than just what is the slope and intercept of a line.